Hello and welcome. In this lecture, we are going to cover another very important statistical technique which is in the same league as PCA and is called PLS regression. Before we learn how to build a process monitoring solution using PLS, let us understand conceptually what is PLS. In the previous lectures, we saw how PCA allows us to find a compact representation of a process data set collected in a single block of X variables. However, many times you will end up working with systems where you will have two blocks of variables, the X variables and the Y variables, where the X variables are assumed to be driving or determining the Y variables. For example, consider this system. Here, let us say we are interested in knowing how does the product purity values and the process efficiency relate to the rest of the process variables. Let's say the incoming feed flow, the intermediate temperatures, the intermediate pressures, and the intermediate flows. In such cases, PLS has been found to be a very effective tool in finding the relationship between the X variables and the Y variables. Overall, just like in PCA, PLS will allow you to capture the systematic variations in the X and Y datasets, quantify the noise present in the input variables, the X variables, and also quantify the noise present in the output variables. Later on, we will see how we can use all these different sources of variations in the data to build our fault detection metrics. Let us see in some more detail how PLS allows us to do so. For that, let us quickly discuss how we can model the relationships between X dataset and the Y dataset. One very obvious approach is to use multiple linear regression or multivariate linear regression via ordinary least squares fit. Note that the Y block can contain just a single variable, output variable, or multiple output variables. Another approach that can be used is principal component regression or the also called PCR. Here, the X dataset is compactly represented via a score matrix T, which is then related to Y via again multiple linear regression or multivariate linear regression. Another very interesting approach that is adopted by PLS, where it first transforms X into the score matrix T, Y into the score matrix U, and then relates the T score matrix to the U score matrix. The trick that is used by PLS is that it finds these score matrices T and U in such a way that it can explain as much variance as possible in the X dataset, explain as much variance as possible in the Y dataset, and the relationship between the X and the Y datasets is maximally captured. Alright, so far you are with me, right? Let us look at the workings of PLS from another prism. Here we consider this 3D X dataset and the 3-dimensional Y dataset. Here note that for each dot in the X space there is a corresponding dot in the Y space. So basically both these dots represent one observation sample containing the X variables and the Y variables. Let us now focus on the task of finding the first component. Here in these diagrams, you see that the direction of the first components W1 and C1 have been highlighted. The original data samples are projected onto these components to give us the score values in the T1 score vector and the U1 score vector. Now, if you remember in PCA, the first component in the X space was found in such a way that the T1 score values were maximized. In PLS, we instead maximize the covariance between the T1 score values and the U1 score values. And we know that the covariance is given via correlation between T1 and U1, the square root of the variance of T1 and the square root of the variance of U1. By maximizing the covariance between T1 and U1, if you notice what PLS achieves is it maximizes the amount of X dataset variations that are captured in T1, maximizes the variation in the Y datasets that get captured in via U1, and it maximizes the correlation between the T1 scores and U1 scores. After you have found out the scores along your first component, if you plot them, you will find a pretty good linear fit between the U1 and T1 scores, unless your process happens to be highly nonlinear. Alright, let us focus now on the second component. Here again, we have highlighted the second component, the W2 and C2. W2 and C2 are again found out in such a way that the corresponding score values in the T2 vector and U2 vector, the covariance between them is maximized. In PCA, we had seen that in the X space, the second component was found in such a way that it was orthogonal to the first component. Similarly, in PLS, this W2 is constrained to be orthogonal to W1, but only in the X space. C2 is not necessarily orthogonal to C1. Also note here that the original data samples are not directly projected onto the W2 and C2 directions to give us the corresponding score values. There's something called deflation step that is involved, but we will discuss that in the next lecture. For now, what I want to emphasize here is that since the components only in the X space are confined to be orthogonal, therefore, the maximum number of components that you can extract in PLS equals the dimensionality of the X space, which is given by the number of X variables that you are dealing with, which let's say equals M. As you keep extracting the third component, the fourth component, and so on, at some point you will find out that it is not worthwhile to extract any further components because it does not give you any further predictive value, that you cannot predict Y any better with the knowledge of any additional principal component. We will see in a later lecture how we can actually determine the optimal number of principal components that we should retain or extract via PLS. For now, let's just know that once you have extracted the components that you want, you can write your Y as a function of U, which itself you can write as a function of the T-score matrix, which you can write as a function of your X data. So therefore, using PLS, you can relate your Y to X. Okay, so overall, what do we see? The T-score matrix that PLS provides you captures the systematic variations in your X and Y datasets, and you can reconstruct your X via T that will provide you or allow you to compute the noise in the input variables. You can reconstruct your Y variables, which will allow you to compute the noise in the Y variables. Later on, we will use this to compute our fault detection matrix. Hopefully, for now you understand what PLS is and what it is trying to achieve. In the next lecture, we will get ourselves familiar with some PLS modeling related terms. See you there. Bye bye.